University of Technology, and in our group we are mostly dealing with dielectrics, and in my project we are focusing on electrical characterization and surface charge dynamic on polymeric insulation materials. And we know that it's a good replacement to traditional insulators, but the problem with the polymer is the surface charging and relaxation, which is an inherent phenomena in HVDC insulation systems. In this project, basically we use different types of HTV silicon rubber materials with different thicknesses, the range of 2 millimeter and nearly 10 times lower, and some of them were filled with ATH, and we try to characterize them using standard methods, using Keith electrometer and a resistivity box where a sample is simply put there and a voltage is applied, and then the current is measured either across or along the surface of the sample. But one can see that for some of the samples it may take couple of days, and waiting for such a long time, if computer shut down or installations are going, you can easily lose the data. So we try to look for alternative methods like using surface potential decay method, and one can see that it fairly provide good agreement with the results of standard measurements, and it consumes much shorter time, like couple of hours. And also the advantages with this method is it's a non-contact technique, and simply at higher electric fields the charges may get injected into the dielectric material from the metal electrode, and this technique simply avoids such problems with the metal dielectric interface. Now also in high voltage insulations, basically materials simply exist in the form of layer, and then they simply interact with each other at the contact area, where what we call interface, and to try to investigate how they influence the surface charge dynamics, I try to combine them, what we call sandwich structure. And then one can see that for like when different materials are combined, then the properties or the charge decay is significantly enhanced. So depending on the properties of the material, it can move in either of the direction. And then to complement those measurements, we even did some dielectric spectroscopic measurement, and one can see that at lower frequencies the permittivity increases quite a lot, and that's an indication of the interfacial effects, because simply when the samples are made in a sandwich structure, and when the charges move along the sample, they get trapped into those regions. And then when we use Maxwell-Wagner, basically because it takes only material property into account, it does not take into account the traps on the surface of the material, so then it doesn't work, and that's what we show by simulations. So that's what all I was supposed to say.
Thank you.